Welcome to T1 Day 3 of Honors Precalculus. Today we're going to be talking about symmetry. What does it mean to be symmetric? Well, the most common phrase you'll run into is same on both sides. Now this is a little bit of an oversimplification because we're not necessarily going to have two sides, but it's the same on two sides, specifically when you have line symmetry. In this case, you're talking about something with a mirror image on both sides. So if someone had exactly the same left and right hand sides of their body, you would have a mirror image. So someone like this, you'd have vertical symmetry down the middle if it was exactly the same on both sides. Now, the other type of symmetry we're going to work with is point symmetry. And this is going to be a little bit different. It's not two sides really. It is rotational symmetry. Rotational symmetry. So it's rotational symmetry. So usually you think of symmetry as this first definition, a mirror image, but we're going to introduce something called rotational symmetry, which is symmetric around a point. So we're going to recall that something is symmetric about the y-axis if it has this property, and we also call it an even function. So symmetric across the y-axis is this line symmetry. So if, let's say, we had y equals x squared, this blue graph right here, y equals x squared, that is symmetric across the y-axis, which is right here, because when you plug in negative x, it doesn't change the output value. So when you plug in negative x, so here's an example point. This doesn't prove it, but an example point, 1, 1. It's also negative 1, 1. When you plug in 1, you get out 1, and when you plug in negative 1, you get out 1 as well. It doesn't matter if the input is negative, you get the same output. So one way to show this is if f of x is equal to x squared, then f of negative x is equal to, well, negative x squared, but a negative x squared is negative x times negative x. A negative times a negative is a positive. So in this case, plugging in negative x results in the same function on the output. So again, it's symmetric about the y-axis. It's called an even function, and it has the property you plug in negative x and you get out the same function. A function is symmetric about the origin, so it's about around a point, is said to be odd, and this happens if f of x is equal to negative f of negative x. So what does this mean? It means, well, you end up with an example function like this. So this function right here, here is an example function, y equals x cubed. It is symmetric around the origin. In the background, you might hear Sadako squeaking a little bit. I'm going to go take that squeaky toy away. So when you look at points on y equals x cubed, here are some examples. 1, 1, 2, 8, negative 1, and negative 2, negative 8. So when you plug in the negative x value, it flips the function. So if y equals, let's say f of x is equal to x cubed, f of negative x is equal to negative x cubed, which is negative x times negative x times negative x, which is equal to, there's an odd number of negatives here. So you're going to end up with negative x cubed, which is the opposite of f of x. So if you plug in negative x, you end up with the opposite. That's what this says right here. Okay, so let's look at some examples. So these want to know whether or not the function is even, odd, or neither and prove algebraically. So you're plugging in negative x. So let's zoom in here and take a look. What happens when you plug in negative x for x? Well, here's x, and I like putting parentheses around it just to be certain, or if it's already in an absolute value. So negative 3, and I'll stay with red here for consistency. Negative 3, absolute value of negative x plus 2 times negative x to the 4th minus 8. Absolute value means distance from the origin. The absolute value of negative x is x, so this is just going to be negative 3 of x. Another way to say that is just the absolute value of x. Plus 2 times, well, this is an even number of negatives right here, an even number, so it's going to end up being positive, so it's just x to the 4th again minus 8. So we end up with the same function. We ended up with the original function. So now we know that f of negative x is equal to f of x. So therefore, that's what these three dots mean. Therefore, even. What happens over here? If we plug in negative x over here, you know, with negative 5 times negative x to the 5th, 3 negative x cubed plus negative x. Do you see all these parentheses I put in? It's really important because it's really just tracking the negatives. One errant negative sign and this whole thing goes down. So now when you do this, just keep track of the negatives. You end up with negative 5, and then there's an odd number right here, so that's going to be times negative x to the 5th. And remember, I almost put it there, it's a negative, so you have, right here you have 3 of them and then a 4th. So you end up with plus 3x to the 3rd minus x. So what do you end up with? Let's clean this up. You end up with 5x to the 5th plus 3x cubed minus x. So what is that in relation to the original? Well, let's factor out a negative, and you end up with negative 5x to the 5th plus 3x cubed plus x. And this right here is g of x. So what do you end up with? Negative g of x. So what happened here? We show that when you plug in a negative x, you end up with the opposite of the function. Therefore, this is odd. Therefore, it's odd. Keep in mind, it's really easy to mess up a negative on this, so practice this. So now we're going to look at what happens as x gets large in both the positive and negative directions. We're going to write this in limit notation rather. So how do you say this? You say this as the limit of f of x as x goes to infinity. This right here is the limit of f of x as x goes to infinity. And similarly, the one right here is the limit of f of x as x goes to negative infinity. X going to infinity means x going real far to the right. X going negative infinity is x going real far to the left. So this is where we get to do something that you might find a little bit uncomfortable, which is do a little bit of hand-waving math, or another way to say it is use pure logic. So state the end behaviors. So what is the limit as x goes to infinity of h of x? Meaning as x gets huge, what happens to the output of this? As x gets huge, what happens? Well, let's look at these 4 terms here. There's this one, the first term, the second term, the third, and the fourth. As x gets huge, I mean billion, trillion, gazillion, how do these 3 things compare? And we'll just label them the first term, the second term, the third term, and the fourth term. Well, as x gets really, really, really big, the only term that's really going to quote unquote matter is this x to the 4th, because everything else is going to be really, really, really small compared to it. So basically, the only term that matters is this first term, because comparatively, these are going to be super small when x gets huge. A trillion to the 4th power is way, way, way bigger than a trillion to the 3rd. So what happens here? Well, x to the 4th in green there is always going to be positive, and then this is going to be negative. So this is actually going to go to negative infinity. And we say equals infinity or negative infinity, but it doesn't actually equal negative infinity. It's going to. That's what it means. What happens over here? The limit as x goes to negative infinity of h of x? Well, the same thing is true in terms of the analysis. When you plug in negative infinity or think about it, the only term that matters is this first term. X to the 4th is still going to be positive, regardless of if you're plugging in a positive infinity or a negative infinity. So when you plug in negative infinity, this first term is still going to be negative 5 times something huge that's positive. So it's also going to negative infinity. So what you know is that if you graph this, as x goes to the right, the function is going to go down, and as x goes to the left, you know that the function is going to go down. That's just the end behavior. Remember, end behavior. This isn't exact, it's just the end behavior. So we're going to do something similar here, even though this is a fraction. We're going to look at g of x, and we're looking at the limit as x goes to infinity of g of x. So again, if x is getting huge, what are the only terms that are really going to matter? The only terms that are really going to matter are these 2 right here. These are going to be infinitely, like really, really, really small compared to those 2 terms. So you can ignore them because these powers are all less. This is x to the 0, x to the 0. These powers are all less than 5. So what happens here as x gets really, really big, and if you're just looking at this, like if you were in algebra 1 and you just had negative 4x to the 5th over 2x to the 5th, what would you do? You would cancel this, and it leaves you with negative 2. That is absolutely what happens. As x goes to infinity, this thing gets infinitely close to an output of negative 2. Now what happens similarly if as the limit as x goes to negative infinity of g of x? Well, in this case, the only thing that changes is you're plugging in negative infinity into this thing, negative 4x to the 5th over 2x to the 5th. Well, again, what happens? It doesn't matter what you plug in. These are still going to cancel. It still leaves you with negative 2. So again, it is negative 2. What this means is when you graph this, as x goes to infinity, the graph gets infinitely close to y equals negative 2, and as x goes to negative infinity, it gets infinitely close to negative 2. Now there's lots of other characteristics, turning points, local mins and maxes, but as x goes to infinity, and, sorry, that's infinity, not negative infinity. As x goes to infinity and as x goes to negative infinity, it approaches this horizontal asymptote of negative 2. And yes, you're going to need to know how to spell asymptote. Asymptote. It's kind of a fun word. So with regard to asymptotes, there are vertical asymptotes, and those are the asymptotes that are straight up and down. And either, as you approach, it's going to be both up, or you're going to see both going down, or you're going to see one going up and one going down. You're going to see something like this, or you're going to see something like this. It's possible that these are the 4 things that can happen at a vertical asymptote. Horizontal asymptotes occur just like what we saw here with regard to end behavior. So, again, end behavior, state the equation of all asymptotes of each of the following. So let's take a look at these functions here. G of x is equal to negative 5 log x minus 4 plus 6. And this is where you get to do the transformation of functions. And remember what log x looks like. Log x looks like this. Oh, and I'll use the red so we can actually transform it. So log x looks like this. And then what happens as you make it negative, let's say y is equal to negative 5 log x, what does that do? It flips it over the x-axis, so you end up with a graph that looks like this. And then what does this do right here, the negative 4? It moves it 4 to the right, 4, and this is up 7. So if we go right 4 and up 7 from here, we end up with right 4. So we're going to have a vertical asymptote at x equals 4. So it's going to look like this. So state the equation of all asymptotes. Well, the original asymptote here was y equals 0 for vertical asymptote, VA, vertical asymptote. Now the vertical asymptote is not y equals 4, x equals 0 and x equals 4. Now what happens? Are there any vertical asymptotes on this one? Well, what happens to this? As x gets really, really, really big, what happens to the output? What's the limit as x goes to infinity of g of x? Well, it's just going to be negative infinity, because this right here, this first term, as you plug in larger and larger numbers, this thing is just going to go really, really, really negative. So in this case, there are no horizontal asymptotes. What about this one right here? Are there any vertical asymptotes? Well, let's factor this first. This is going to be, let's say, I don't know, we could factor out a 2 and make it 2 times x minus 3, and then it's 2 times x squared minus 9. So that's 2 times x minus 3 over 2 times x minus 3 times x plus 3. And what you'll remember or realize is when you cancel, this means there's going to be a hole at x equals 3. So what does this leave us with? 2 over 2 times x plus 3. So what does that mean? Well, it means that down here, what's the only thing x can't be? X cannot be equal to negative 3. Because if x is equal to negative 3, you have a divide by 0. That means there's going to be a vertical asymptote at x equals negative 3. And what about the end behavior? What's the limit as x goes to infinity of f of x? Well, again, we look at all the powers here. The power of the numerator is 1. The power of the denominator is 2. As x gets big, this is the only term that matters, the denominator. Everything else is going to be much smaller. So what's a small number over a huge number? Small over huge, as huge gets really, really big, is just going to be 0. So the output is tending to 0. So the horizontal asymptote is y equals 0. And the same thing is going to happen when x goes to negative infinity, because when you plug in negative infinity into this, it's still going to be positive. It'll approach from a different side, but it'll approach y equals 0. This will take practice. The last topic for today is concavity. And we're going to say a function is concave up if its rate of change is increasing, and it's concave down if its rate of change is decreasing. So what that means is, what's going on here, the rate of change in calculus, as a preview of what's to come, is the slope of the tangent line. Is it getting steeper? This is getting steeper and more positive. It's getting steeper and more positive. So this thing is increasing in concave up. This is increasing in concave down because its slowing down. The slopes of these tangent lines are getting smaller. What about here? Decreasing and concave up. It's decreasing and concave up. These tangent line slopes are getting smaller. And what do we have here? We have the same thing. This is decreasing and concave down. These tangent lines are getting steeper and steeper down. Another way to think about this is, its concave up is a smiley face. Concave up is a smiley face, and concave down is a frowny face. Concave down is a frowny face. So what do we have here? We have concave down because these are parts of a frowny face, and we have concave up because these are part of a smiley face. And when I say part of, I mean these parts right here. These parts right here. So we're happy. Concave up is happy. Concave up is happy. Concave down is sad. Just one way to remember it. My Algebra 2 teacher taught me that a long, long time ago, or my Precalculus, I can't remember. It was all mixed up back then. So on this function, we estimate where the function is increasing, decreasing, concave up, and concave down. Now it's going to be increasing from that lowest point to this highest point. So we could label it. And again, we don't have the function, so we only estimate. So we'll call that point A and we'll call that point B. A looks like it's about the point 3.7, and B looks like the point, I don't know, negative 1.5 comma negative 3. So it's increasing from from negative 1.5 to 3. So then where is it decreasing? Well, it's going to be decreasing everywhere else. So there's two places it's decreasing. It's decreasing negative infinity to the x value of b, which is negative 1.5 union of 3 to infinity. Remember, these are intervals. Intervals, not points. These are intervals. Okay, what about concavity? So where is it smiling? Well, it's smiling, and I'm not going to do it on here because I want the colors to remain. It's smiling from here to here. So it's smiling, so this is concave up, from there to there. So something happens right about in the middle here, and then it's frowny face on the purple. So what does that mean? It's concave up to this point. We'll call it point C. C we'll estimate to be on a 1, 2.5, about that. So it's concave up. It's smiling from negative infinity to 1, and it's concave down from 1 to infinity, assuming this keeps on going. So we just had to estimate because we didn't have a function to plug into our calculator. If we had a function to plug into our calculator, we could use the max-min features to get this point. Now, finding on your calculator this point's a little different, and right now we're just estimating it.